Okay, I've been getting a lot of questions about understanding what errors are and how errors are supposed to help you interpret what a hypothesis test means. So I thought I'd try a little different strategy here. I'm going to do a two-parter here on errors, type 1 and type 2 errors, the concept of effect sizes and power. Part 1 here is just a review of the two types of errors. And I want to show you how the first two steps of a hypothesis test really determine what is an error and what is not. So let's take a look at this. This is just a screen I've shown you a few times. Then the first two steps, what we do is we just say that, well, we already know about a population, and this is what we expect our samples from that population to look like. This would be a weird sample to get, something over here in the tails. So if we wind up with our sample in the tail in our experiment, it's probably from some other source than that population. So anyway, let's look at this. This is my population. It has a mean of 70.08, standard deviation of 9. That's supposed to be a standard deviation right there. And I'm sure that you're familiar with the sampling procedure. We take samples from the bowl. Here I've got a sample of 8 individuals taken haphazardly from the bowl. And I'm going to work a little bit of magic here. And there we go. Have a little histogram. It turns out that that group of 8 has a mean of 74. I know the population had a mean of 70, so our group is only 3.92 beats per minute higher than the average. So our sample had a slightly higher heart rate than the population. And that's not too much error. And actually, we know more or less how much error to expect. We probably will find something like that on average. In order to estimate what we should expect, though, what we can do is create or estimate what the distribution of sample means would look like. So what I've done down here is I've taken the mean of this group and I've plotted it down there. And if we kept taking samples of 8 and plotting them over and over again, we would expect on average that they would vary by about 3.5 beats per minute. This is our standard error. It's our standard deviation of 9.9 from the population divided by the square root of the sample size, which is 8. So if we kept taking samples of 8, the sample means would usually be 70.08, give or take about 3.5. All right, now with that, do this over and over again. You start to have the sampling distribution here. We saw using the central limit theorem that that's actually quite predictable. Let's take a look at this in more detail here. I'm going to blow this up. Okay, so if I know what the standard error is, and I know what the mean of the population is, I can build a confidence interval. And a 95% confidence interval would fit right there. And as you can see, that most of the sample means that we would take don't fall within that range, or do fall within that range. I actually have 16 samples plotted there, and all of them fall within the confidence interval. Now, if we kept doing that, 5% of our samples, that's about 1 in every 20, will wind up out here, and that's okay. Let's see, so how does this relate to hypothesis testing? Well, make a quick transition here. So for our test, we've been using the stair climbing example. So I'm going to start with the null hypothesis. I know that in our class, people have a resting heart rate that should produce samples in this range right here. So I set an alpha of 0.05. That means there's 95% in the middle, and my alpha is split with 2.5% here and 2.5% there. So that's my alpha. I know that from this bowl, that's where most of my samples will be. Now I've got an alternative. This alternative is that people might have come from climbing stairs instead. Okay. Now, the way I decided to animate this is to emphasize that we don't really know what is happening. in the real world, and we're using science to try to make inferences about it. So here we go. In step 3, what happens is we wind up magically with a sample. That sample turns out to have a mean of 78. So in case you missed that, that was my illustration of what sampling is. All right, so we have 78. When we conduct hypothesis tests, what we do is we convert that to the standard score. Here I'm doing a z-test. The z, can't really see that behind the subtitles, is 2.1 z. The critical value is 1.96 z. All right, so in step 4, our question that we're trying to answer is, where did that 78 come from? Knowing what you know about the null hypothesis, that if we take samples of 8 from there, it should fall within that range. So it looks to me, because our z falls way out here outside of that confidence interval, it's highly unlikely that it came from here. So I'm going to reject that null hypothesis, and I'm going to say, because this z-score falls outside of the 1.96 confidence interval, it probably came from here instead. So what did I do? I rejected the null hypothesis, and I said, I believe that the means are different. Now, I don't know. To be honest, I don't know if that's really true or not. And as mere mortals, we never know. And that's why I created this idea of the TED, the god of statistics, who knows the truth with a capital T. Now, if we had the chance to visit the Oracle of TED, and he told us what the truth is, we could say, hey, we rejected the null hypothesis. And he might come along and say, no, that's a type 1 error. The means are really the same. In this case, that would happen if I took the bowl, this bowl here, and my sample actually came out to 78. If my mean was 78, that could happen. I would reject the null hypothesis and say that something happened to change the heart rates, but we would be in error. Now, type 1 error really just comes from alpha. So there's a 5% chance of that happening, because my alpha was 0.05. Typically, though, when we make that decision, we're going to be correct. Okay, so when we reject the null hypothesis, we're going to be correct most of the time. We're going to say the means are different, the groups really are different, and we'll be correct. All right, so that's what a type 1 error would be. We don't know ever for sure if we've done it or not. We only know that it's going to happen about 5% of the time. So what is this other kind of error? Let's take a look at another test. So this time, if we pay close attention, TED will show us where the sample comes from. Okay. Wow, that was a lot faster than I thought it would be. Okay, I saw that sample coming down the stairs. It fell down the stairs, and maybe that had something to do with its heart rate. This heart rate of 75%, that's an average of 8 people, is 75 beats per minute, sorry. The z-score for that is 1.6z, 1.6z. If you take a close look at this, our confidence interval stops at 1.96z. This actually falls within the range. Now, even though I saw it coming from the stairs, that actually looks very much like what I would expect if it came straight from the bowl. So it leads me to believe that we must fail to reject the null hypothesis. This is not really that different, and it's not unusual. Now, it could be, in that case, that stair climbing is no different than sitting in class. Let's take a look at this. In this case, because my score fell within the confidence interval, I failed to reject the null hypothesis. If we go to TED and he says, you're correct, stair climbing doesn't change anything, then we would be right. And that's satisfying. It's good to be right. But that's not nearly as satisfying as up here where you're actually showing something's different. So correct is good, but not the best kind of correct. Now, we failed to reject the null hypothesis. There is a chance that we made the other type of error a type 2 error. And a type 2 error simply means that I said that the sample we found is likely to have come from the null hypothesis population. In fact, it was just an unusually low sample from the people who climbed the stairs. Now, again, that's kind of a probability thing. We don't ever actually know the truth with a capital T, the same level of certainty as a supreme being would. But by using good statistical techniques, we can actually keep type 2 errors to a minimum. And that'll be the subject of the part 2 of this series. So I hope that gave you something to think about and another way to understand what the errors are. Errors are part of all hypothesis tests. Any hypothesis test can have a type 1 or type 2 error. We're never sure if we got it right or if we've committed one of the errors, but there are ways to control them. So that's coming up next.